Okay, I think we can go ahead and get started now, since it's 12:05. So everyone can see the slides, right? Okay, awesome. So thanks everyone for joining this month's Grundfest Memorial Lecture. Before we start, just a few notes. The talk usually begins around 12:05 and will end a bit early for questions. And if you want to follow along with future talks, you can visit this website that's on the slide. So this lecture series is hosted in remembrance of Professor Warren S. Grundfest, who was a professor of many disciplines at UCLA. And he was also a SPIE fellow in biophotonics and a pioneer in many imaging modalities. Professor Grundfest was also a strong advocate of junior scholars, which has inspired this lecture series' focus on highlighting early career researchers in the field of computational imaging. I also want to thank the co-organizers of this lecture series, Professor Chuda Kadambi at UCLA, Professor Katie Bauman at Caltech, and myself and Pradyumna Chari, who are PhD students at UCLA. Lastly, I also want to thank the sponsor of this lecture series, Akasha Imaging, which is a computational imaging startup on polarization. Akasha sponsors an inverse honorarium, like I said, highlighting early career researchers such as PhD students and postdocs. So with all that, I would like to introduce this month's speaker, Mark Sheinin, who is a postdoctoral researcher at Carnegie Mellon University. Today, he'll be telling us about his work on computational imaging for sensing high-speed phenomena. And I'm sure we're all very familiar with Mark's work, so I will go ahead and pass it over to Mark so he can tell us a bit more about this.
Okay, give me a second. Here. All right, can you see my screen? Oh, sorry, I forgot again to share with sound. So it's always share sound, yes. Okay. Cool. So thank you for the introduction. And yeah, today I'm going to talk about high-speed imaging, but also stay tuned for the reflections part, because I've prepared some special slides for you that I call 5 rules for becoming a 10% better researcher. It's everything I could think of that helped me to become a better researcher, and I hope to pass it along here. Okay. And as you know, or probably know, my field of research and interest really is computational imaging in the context of computer vision. Now, the original goal of computer vision is to give the machine, the ability to sense and understand the environment just like a human can. And this is why we equip the machine, our artificial mind, with an artificial eye that is very similar in principle to the human eye. But human vision has a limited capability of sensing the world. So somewhat tragically, we are blind to many interesting phenomena that are happening all around us, like things that happen beyond the line of sight, things that occur really fast, lights outside the visible spectrum, and more. All these phenomena are simply beyond the reach of human vision and require superhuman vision, as Ramesh Raskar puts it. And this is why computational imaging is so exciting, because it allows us to build novel vision systems to sense and reveal this hidden phenomena. And I say vision intentionally, because we need to reinvent both the eyes that see the scene and the brain that processes these weird images that our new alien eyes produce. Now, in this talk, I'm going to focus on one such superhuman vision task, which is imaging very fast phenomena. Now, in the same way that the human eye can only see a small sliver of the electromagnetic spectrum, so does the persistence of human vision limits our perception of fast events. Events that are so fast, they can happen in the blink of an eye, which motivates us for developing high-speed imaging to catch these fleeting moments. Now, despite a lot of progress in sensor technologies, it's sad that most of our cameras are not much faster than the human eye. But have you thought about why is that really? I mean, your smartphone can easily capture an image with a very short exposure. So why can't it capture a video at the same speed? And the answer is that capturing high-speed videos with high spatial resolutions is fundamentally challenging. So roughly speaking, high-speed imaging is challenging because of two factors. First, the maximum frame rate of a camera is limited by the bandwidth that is required to read out, digitize, transfer, and store that huge amount of pixel data. So for any given camera, if we want a higher frame rate, we have to reduce the amount of pixels we read out per frame. Now, obviously, that's not great, because to get high speed, we have to sacrifice spatial resolution. And secondly, high speeds require short exposures that can significantly reduce the SNR. So today I'm going to talk about 3 projects that use computational imaging to overcome these challenges and open our eyes to high-speed phenomena. In the first project, we will see that lights that are all around us that appear static are in fact full of life and are flickering in interesting ways. We'll understand why these lights are flickering, how to effectively capture this flicker using the ACam, and what type of new information this flicker reveals about the scene. Then I will present a novel computational imaging system principle called Diffraction Line Imaging that combines diffractive optics with 1D sensing to achieve high speed and high accuracy imaging of sparse scenes, as well as a totally new way to do structural light 3D scanning. And in the last project, I will present a novel camera that can capture tiny, high-frequency surface vibrations, such as the vibrations of musical instruments and the vibrations of a chips bag reacting to the sound of a nearby speaker. And in the last part of my talk, we'll explore the short-term and long-term future directions of all these research threads. So let's start with the first project and talk about artificial lights. So like any good story, the story of this project begins when a crazy idea occurs to my PhD supervisor, Yoav's head. You see, Yoav is kind of an amateur astronomer, and he wanted us to build a camera that would enable astronomers to image the night sky from a busy metropolitan area. But as you probably know, if you look at the stars in the middle of a city, you don't see them. And this is because the weak starlight that reaches our eyes and cameras is mixed up with artificial light that bounces back from the atmosphere. But as electrical engineers, we knew that most of these artificial lights are powered by alternating current. So we wondered, what happens here, where the AC voltage crosses the zero and is thus very low? Is there a brief moment in time where the lights are dim enough for us to capture the stars? But you see, capturing this moment with a high-speed camera is not going to work, because the required short exposure would create an image with very crappy SNR. But we had an idea of how to overcome this problem. All we needed is to build a camera that could collect signal from many such moments during a single long exposure. And that's how the ACam, a camera specifically designed for imaging under AC illumination, was born. And once we had the prototype, I took it to the Technion's roof, pointed it at Haifa Bay, and captured a video. Surprise, surprise, this is what we got. And you can see there's no moment of darkness, and the lights seem to be flickering with different phases. So after further investigation, we realized that different bulbs flicker differently. But as it turns out, this temporal structure that is hidden from the human eye is not a bug, but a really strong feature. So to understand why bulbs flicker, we need to do a quick 3-slide crash course on the electric grid. So the AC voltage that powers everything in your house comes from power plants in 3 phases separated by 120 degrees. And this voltage is approximately a sinus of frequency 50 or 60 hertz, depending on the country. Different bulb types connected to the same phase have different flicker profiles, and that's the key. We call a single period of this profile as the bulb response function, or BRF. Now, connecting identical bulbs, the exact same bulb, to AC phases 120 and 240 causes a corresponding phase shift in their response function, which means that we can treat the scene as having 3 different sources, each with its own unique temporal profile. Okay, so what can we do with the BRF? Well, the first thing we can do is to identify bulbs in the scene. Okay, so here's a flicker we measured for this bulb. And if we have a data set of bulb response functions, we can use it to identify not only the bulb type, but also its AC phase, its electric grid phase. And because we have a camera, we can do this type of bulb type and phase recognition in the scale of a city. And it turns out that this phase information is kind of valuable for power grid analysis and monitoring, especially in developing countries such as sub-Saharan Africa and India. Now, things become more interesting, more visiony when we look at things like this, where multiple lights are all mixed up together. So how can we leverage bulb flicker in this type of scenes? Well, let's look at an example. This is an image sequence captured using our ACam system. This sequence spans the flicker cycle, but it might be hard for you to see the flicker, so let me digitally amplify it. This is how your rooms look like, okay? Now, using our bulb dataset and an image formation model under AC illumination, we can solve an inverse problem and recover the single source images of the scene. Now, these single source images are really cool because they reveal how the scene would appear in a standard exposure if only that source was active, if we went and turned off all the bulbs of the other sources. Now, you'll notice that in this scene, we decompose the scene into 3 sources. And these 3 sources correspond to the 3 AC phases that powers the ceiling bulbs, which are all of the exact same type. Now, once we decompose some scene, we can recompose it using different bulbs from our dataset. For example, here we simulate an image that shows what happens if you take all the bulbs connected to phase 240 and you swap them with sodium street lamps. This is how the scene would appear. Now, we've explored the ACam in many, many scenarios, including indoors, outdoors, a mix of indoors and outdoors, where we separate a scene that has both static sunlight and flickering indoor lights. We used it with a single frame, and we even used it in real time. So all of these scenarios, the ACam was working. Now, so at this point, you might be thinking, okay, cool, this ACam is pretty useful, but like, where can I get one? Well, look no further than your pocket. No, I mean your other pocket. So it turns out that under modest light conditions, when the scene is not too dark, we can turn any rolling shutter camera into an ACam. So let me explain. In each frame, the rolling shutter sensor exposes the scene from top to bottom, such that each row samples a different time within the flicker cycle. So now, given many frames, we can sample each row across the entire flicker cycle. Then, by computationally figuring out the exact synchronization between all the frames and all the rows, we can reshuffle this entire video and get the full flicker sequence of the scene. Okay, so any questions for the first part? All right. So in the previous section, we exposed some interesting behavior of the static lights that illuminate our environment, the bulbs in this room. But in computer vision, we also use light sources as strong visual markers. Such markers can be found in motion capture suits, night scenes, and structure light 3D scanning. Now, in all these applications, our vision goal is to find the position of these markers in the 2D camera image plane. But as we've discussed in the intro, capturing these markers for fast-moving objects is hard because of the limited camera frame rates. But as you can see, at high frame rates, these markers occupy the image plane very sparsely. So capturing the entire 2D image for these sparse markers is very wasteful. And the question arises, can we design an imaging system that is more efficient for this task? So here is a radical idea. Let's save tons of bandwidth by throwing away most of the camera pixels and only reading out a single image column. And since we're only reading out a single column, our camera can operate much faster. In fact, we now effectively have a 1D camera, also known as a line sensor. Okay, great, but how can you use a 1D camera to recover 2D positions? Sounds kind of hard. Well, the key idea is to image the scene through a diffraction grating. So a diffraction grating is just an off-the-shelf optical filter that, much like a prism, disperses light into its spectral colors. Diffraction gratings are used to create artistic effects, and they're also used in many scientific applications. So in our case, the diffraction grating disperses the lights from the points, creating horizontal rainbow color streaks on the 2D image sensor. For every point, the streak's vertical intersection with the 1D sensor corresponds to the Y position on the 2D image plane, while the point's X coordinate is now encoded by the measured color at the intersection. So how can we use color to encode position? Let's dig in a little bit more. When an incoming beam of light enters our grating at some angle theta in, each wavelength or color exits the grating at a different angle theta out. The relationship between these two angles is given by the diffraction grating equation, where d is a parameter of the grating's microstructure and lambda is the wavelength. Next, let's put a camera to measure the color at a fixed angle, which corresponds to some sensor column. Now, for this fixed angle, the diffraction grating equation gives us exactly the relationship we're looking for. Namely, for every color that we measure, what was the light's incident angle? Which means that we can solve an inverse problem and compute the X coordinate from the measured color. Now, in practice, we use a learning-based approach to learn this inverse function directly to account for many other physical factors that we don't want to deal with analytically. Now let's look at another example. So here's a fan, the fan from before, mounted with 2 LEDs and rotating at 1,000 RPMs. Now on the right, the white dots, the white LEDs, were captured using a 2D camera that is capturing at its maximum speed. And in green, we overlay the point position recovered using the same camera, but with our system, and 16 times faster. Now, in addition to looking at points, our system also works for vertical lines. And this is very useful because we can use it for fast 3D line scanning. So here, we see an object being scanned on the left, the view from the sensor plane in the middle, from the whole plane, and the sensor line measurements being stacked on the right. And here's the recovered shape using a standard 2D camera. And here is our result using a 1D sensor. Now note that to the best of our knowledge, our system is the first structural light system that uses both a 1D source, a line, and a 1D camera, a line. Now, so far, we made an assumption that the column measured at each line sensor pixel belongs to a single scene point and can therefore be mapped directly to that point's x coordinate. Now, while in some cases this assumption makes sense, there's a whole class of denser scenes where this assumption basically doesn't hold. And by the way, these scenes are denser than the scenes that I've shown you so far, but they are still very much sparse with respect to the full 2D sensor. So in these denser scenes, most of the time, what we measure is a mixture of the rainbow colors. And the more mixture we have, the more we are prone to signal saturation. So just naively applying diffraction line imaging to these scenes will fail. So how do we solve this problem? Well, since a denser scene means more information to recover per frame, we need to be a little less radical and gather additional information, additional signal from our sensor. How much more, you might ask? Well, more than one column, but still a fraction of the full sensor to maintain a high frame rate. So to adjust our system to the new assumptions, we define a convolutional image formation model for our sparsely sampled images and use it to solve an inverse problem and recover the scene. Now, I'm going to skip the model and the recovery details, but you can find them in our ICCP paper. I will mention one interesting detail about this new model, and that is that it supports arbitrary diffraction points for functions, like a star PSF that is created if using a double axis diffraction grating. So we tested the system in various scenes with high-speed motion, including high-speed motion capture, PIV, particle image velocimetry, and imaging combustible particles like sparklers. Now, I don't have time to show you all the results, so I'm just going to show you my favorite one, which is this motion capture scene where I'm wearing a motion capture suit and I'm holding a rope that has motion capture markers, and I'm doing a fast rope skipping exercise in which the rope makes 2 passes under my feet per jump instead of just 1. By the way, this is called a double under. So here's the video of the action as it is captured using our camera at 1,000 FPS. Now, all our camera is reading out is these 8 columns, okay? And here's the recovered sequence sped up to mimic 30 FPS and here is 1,000 FPS. Now notice the first revolution of the rope under my feet. And we're still going, I'm still in the air. And here is going to be the second revolution of the rope. Okay, so any questions about this part? Okay, if not, I'll continue. All right, so the goal of this last work that I'm going to talk about is to build a camera that can see vibrations. So why do we want to see vibrations? So imagine your best friend, Bob, asks you to record him at his gig at the pub, okay? Now, Bob is a great musician, but the problem is he recently started performing with his friend Alex, who kind of sucks at guitar. So your camera has no trouble seeing each guitar separately. In fact, just like with your own eyes, your own vision system, you can choose to look only at Bob's guitar, while not being distracted by anything else in the room, or only at Alex's guitar, or both. But your camera microphone can only hear a mixture of both guitars. Even worse, the microphone picks up unwanted sounds, such as room echoes and ambient noises. But what if you had a camera that could see the tiny vibrations of each guitar? Then you could record Bob's guitar separately. While being insensitive to Alex's guitar and to the ambient noises. But imaging these tiny vibrations poses two major challenges. First, the small vibrational amplitudes require a powerful zoom lens, even for nearby objects. Secondly, the frequencies of speech and music are, of course, way too high for a regular camera and require an expensive high-speed camera, not to mention a high-power illumination to compensate for those short exposures so you can get a good SNR. Now, there has been a lot of excellent prior work that use such passive visual vibrometry for various tasks. But as we just saw, a passive approach becomes very challenging as the frequencies increase and the vibration amplitudes become smaller and smaller. So in this project, we build a novel dual shutter imaging system for sensing low amplitude, high frequency vibrations using only regular low-speed cameras. Our method can sense multiple points simultaneously and can also support object motions, such as the natural motions of a guitar player. So next, we'll see how to overcome these two challenges and then see some cool experimental results. So in contrast to passive methods, we amplify these tiny vibrations using an active approach called speckle-based vibrometry. In this method, the vibrating surface is illuminated by a laser, but instead of being focused on the object, the camera is focused at some distance between the object and the sensor to image a random interference pattern called speckle. Now, this image speckle pattern is highly sensitive to the surface vibrations, which cause it to shift in the image plane. So the low amplitude problem is solved. But unlike prior methods, our system recovers these 2D speckle shifts at high speeds without using any high-speed cameras. Instead of a high-speed camera, our system simultaneously captured the scene with two low-speed cameras equipped with a rolling and a global shutter sensor, respectively. While the rolling shutter camera itself, as we already saw, is low speed and can only capture frames at 60 FPS, the individual rows of the rolling shutter are exposed one by one, sampling the speckle at high frequencies of tens and even hundreds of kilohertz. Now, we don't want to miss rolling shutter rows, and so we add a cylindrical lens to the optical path that spreads the speckle vertically. This also means that we can sense multiple scene points at once, where each point creates a separate image plane speckle column. So our rolling shutter camera is great. It captures these 1D measurements of the speckle at high speeds. But remember that what we want to recover is the speckle shifts in 2D. So as if we had a conventional high-speed camera. And this is where the global shutter camera comes in. The global shutter camera provides reference frames of the undistorted speckle pattern. And using these reference frames, we can locate the shift of every rolling shutter row by searching for that row intensity profile in the reference. And if we repeat this process for every rolling shutter row, while enforcing some smoothness between neighboring rows, we can get the desired 2D speckle shifts. And by the way, these musical instruments, they don't just vibrate, they can also move, like this violin being played by a musician. But luckily, the global shutter camera also tracks this low frequency speckle motion and extracts the musical vibrations, even for non-static objects. So that's the main idea behind the dual shutter system. Let's see some results. And let's start by getting some intuition from the dual shutter videos of a very simple signal. Just a speaker playing a series of tones doubling in frequency. Now, the video will play in a second and you'll simultaneously hear the input tones. So see if you can spot the different frequencies in the top rolling shutter video. As you can see, our system can recover this perfectly. Now, let's try a more complex signal, okay? This is a song, a typical pop song that has many frequencies. Let's hear how it sounds. As you can hear, the recovery is pretty good. And now, let's increase the complexity level even further by recording these two speakers at the same time, while each speaker is playing a different audio file. Now, just like in the guitars example at the beginning, the microphone has no choice but to record a mixture of both speakers. But our camera system captures each speaker separately, yielding unmixed recordings. Now, we can also record the sound of a speaker from the tiny vibration it creates on a nearby bag of chips. So here, in this slide, we show our method improves the audio quality compared to Davis et al.'s reconstruction from their famous paper called the visual microphone. So let's start by hearing Davis et al.'s reconstruction.
Mary had a little lamb, which was white as snow. Everywhere that Mary went, that lamb was sure to go.
And here is our result.
Mary had a little lamb whose fleece was white as snow, and everywhere that Mary went, that lamb was sure to go.
Now, this is not a precise apples-to-apples comparison, but I think it gives you a good idea about the difference in quality between these two methods. So there are additional results that you can find on our project page, where we use our system to record various musical instruments, and where we use it to analyze the vibrational modes of an object by measuring multiple points simultaneously on that object surface. So any questions about the third project? All right. So let's talk about what's next. Okay, let's explore some immediate and long-term future directions for these projects. So in all these projects that I've mentioned today, I think we've only scratched the surface of the true potential of these methods. And therefore, it's going to be easy to generate immediate future directions by extending the signals we capture, generalizing the algorithms, and scaling up the projects. So, for example, by making the ACam more sensitive, we might be able to detect more than just AC phases, but also other more subtle effects on the electric grid, such as harmonic distortions, which caused equipment malfunction, slide phase and frequency variations that can alert of an imminent voltage collapse, grid security threats, and more. In diffraction line imaging, instead of using a simple off-the-shelf diffraction grating, we can design our own custom diffractive optical element that can not only improve the reconstruction accuracy and enable denser scenes, but might also encode additional information per point, for example, like the point Z coordinate. And in vibration sensing, we can extend the camera to measure the full 6 degrees of freedom of the point, and we can also extend the sensing for a grid of point. These two features, by the way, would really enhance our ability for analyzing material properties and recording many sound sources. Now, we can also generalize these methods and ideas in interesting ways. So here's another crazy idea. Why should the ACam only look at bulbs, right? I mean, bulbs are just one type of electrical device that's connected to the grid. But there are other devices that are powered by the grid, which we can sense remotely to analyze it. And not necessarily even devices that emit light, but perhaps devices that react to the grid with a different measurable signal. So for example, vibration. And luckily, I know just a sensor to measure these vibrations. And speaking of our vibration measuring sensor, our initial paper, the one that we published this year, focused mostly on audio signals. And we haven't really explored the kind of cool fact that our signals are in 2D. So here's a little teaser from an ongoing project where we use the simultaneously 2D measurements at multiple markers to localize the source of a knock by modeling the transient elastic wave that knock generates. And we can also scale these projects. So for example, I would like to see the vibration sensing camera be scaled to capture the whole ensemble of players like an orchestra, or on the flip side, in the industrial side, to measure many machines on a factory floor. And if we build an ACam that can operate from a vehicle in a Google Street type of way, we could perhaps map all the light sources in the country and do grid analysis on a national level. Now, beyond these immediate directions, there is actually a common insight from today's talk that I believe can be applied more broadly. And this insight is that instead of simply imaging the scene, like most cameras do, we treated each video frame as a general purpose bucket of information to which we can encode light from the scene in different ways, depending on the specialized imaging task that we want to do. So for example, in diffraction imaging and vibration sensing, it was clear that we don't need the entire frame to extract the low-dimensional desired output. Therefore, with the right optics, we could trade off spatial resolution for temporal resolution by reading out only a line at a time. But for the ACam, we had to do the exact opposite, right? Since a single frame did not have enough signal per pixel. So here we traded off temporal resolution for spatial resolution by integrating multiple time instances to get a better image SNR. Now, this insight raises some interesting theoretical questions that I don't think have been answered yet. So can we quantify this trade-off exactly using physics and information theory? Can we then use this analysis to design the optimal imaging system per some given specialized imaging task? And how does this analysis change when we take into consideration some network that's computing some downstream vision task? Now, before I conclude, I want to go back to the discussion from the beginning and tell you once again that I believe that computational imaging is most exciting when it uncovers new information about the environment beyond the scope of human vision. And in this talk, we focused on one such domain, which is sensing high-speed phenomena. But in the long term, I think that we should continue to explore this space and understand how far we can push our novel vision systems. So, for example, can we create a system, a camera that captures the sound at every pixel so we can simulate the experience of being in a jungle? Or a camera that retrieves the material properties at every pixels to tell us exactly how furry this dog is. Or a camera that can see the stars from a large city, just so we can make you happy. And with that, I want to conclude and acknowledge all my wonderful collaborators. You can find everything I talked about today on our website, and thank you for your attention.
Let's give Mark a round of applause for his great talk. And I know you also wanted to do your advice section. Do you want to jump into that now, or
is there questions about the talk? Maybe there's.
Yeah, I saw a hand raised earlier, so you can unmute and ask a question if you have one.
I see Katie had a question.
Hi, yeah, great talk and awesome work. Just quick question about the last part of your talk. When you were talking about how you're invariant to the large changes, like with the violin moving back and forth, are you able to tune like the frequencies that you are most sensitive to? Does it have to do with like the speckle that you choose or anything along those lines?
So what we do is we get some vibration signal, and this vibration signal looks like something low frequency. And when you zoom in, just like I did, you actually see these high frequency vibrations. And basically, our system is able to measure everything below the top frequency, which is 63 kilohertz in this case, all the way to very, very low frequencies. And what we do to play the musical vibration, we just do some high pass filtering and play and remove these little things, which you would not hear anyway if you just play them.
But if you use like a red laser versus a blue or something, there's no significant difference in the frequency.
Oh, yeah, okay. Now I get it. So definitely your optical system that you configure is going to affect how big the speckles are. Basically, it's going to affect about the appearance of your speckles. So sure, you want to have, ideally what you want to have is speckles that are very high frequency, not too low frequency, for example. And yeah, that gets challenging, for example, if you try to go too far, you know, if you are like 10 meters away, 20 meters away, the speckles get large and you have to have a larger lens to collect, you know, to have a larger angle.
Okay, cool. Thanks.
Yeah, more questions? Yeah, I can read it back.
Are we selecting among the people here?
I guess whoever talks.
Okay. First of all, this is wonderful, wonderful work. I especially admire the long-term vision and where you're going. So I have two things. One is that related to the previous question, I would suspect that with the movement of the surface for the vibration camera, that the displacement of the surface itself is going to be changing the speckle. Did you find this to be much of a problem? You have ideas of how that might be addressed?
Yeah. So first of all, absolutely. If you move the object just half a centimeter to the left, the speckle is completely different.
Even within the vibrations.
Even within the vibrations, it's true. It's true. And that is why we have the global shutter camera. So the global shutter camera is constantly keeping track of this of the speckle where it is at this moment at a low frequency, but at a frequency hopefully fast enough for us to sort of use wherever you are within this vibration. And actually, I haven't showed this here in this work. For every rolling shutter frame, we use something like 15 global shutter frames and take wherever the signal is best at and combined everything together. So yeah, for sure.
And that sounds quite promising. There's also been some work, I'm not sure I should talk about it yet, of ways that controlling the speckle itself might be possible. But the other thing is this, you're marching into something I've long dreamed of. There have been for half a century, some of the very best microphones are ribbon microphones, in which you have a suspended small membrane that vibrates with the incoming waves. But really, it seems that what you would want is roughly a meter-sized membrane, and as you say, a big grid of movements, and ideally 2D or even 3D movements of the points, because it seems like what you would really want is to capture the wavefront coming in. So essentially what you want for the ultimate microphone is a kind of an audio holography. And this, this to me would seem like the ultimate in the quality and selectivity and signal capture of audio. I mean, right now we're still doing, we're still in the early stages of this, but I wonder if you could comment on what you see as, do you think such a thing might be reachable by these optical techniques, or do we have some theoretical limits here?
So Jack, you could not have stated better a project we are thinking about. You just stated it one-to-one precisely. And I'll just repeat, like all these microphones have a problem where the membrane has to move some physical object and it will basically ruin up some frequencies. And if you have a floating membrane, that would be sort of the ideal microphone. And if you have 100 floating membranes in exactly the same configuration that you said, it will probably be even better. There's nothing more that I can say about it. You're spot on and as a possible application for this technology.
Your secret is safe with me. But
with
wonderful. I'm cheering you on. Let's go for audio holography.
All right. So maybe one more question, and then I'll get to the 5 rows. Nelson.
Yes.
I'm just
Mark,
picking the person that is on top of my Zoom list, like
yes.
the video, I guess. Yeah.
Mark, thank you for your amazing presentation. I'm curious about maybe to make more compact the architecture that you show, which is which capture the vibrations. I think that is possible. Maybe I want to ask you first, remove the global shutter and just do the whole work with the rolling shutter. For instance, imagine that you can't recover the global shutter signal, and then, well, this is this involves changing the how the rolling shutter works, but it's like make a shuffle in the rolling shutter positions. Do you think could be?
Yeah, so the problem is that in whichever order you will rearrange the rolling shutter, you end up with a signal that just looks like more speckle, basically. So you have imagine a scenario where your object is moving with the same sort of let's say with a regular rolling shutter, it's moving down with the same speed. You will just get almost a constant image, and there's really no way that I can think of right now to decode that image without having the information of how this speckle looks like undistorted. The global shutter actually plays a big role in the sense that it provides the map, and then the rolling shutter is just telling you like, you need to go to this Starbucks or that Starbucks, and just without the global map, you just have a Starbucks and you don't know where to find it in reference to anything else. So if you can find a way to only do it with a rolling shutter, that would be awesome. I can't really think of one right now.
Well, maybe it's possible. I'm going to share one link with you. Maybe could be.
Yeah, so send me anything you want. You have my email, and let's talk.
Okay, thank you very much.
All right, cool. So I guess now I'll get to the other part of the talk, the reflections part, and I have to say, I really enjoyed this part in the Grundfest lecture. So I wanted to do my part, and I had to do some real thinking for this part because a lot of the advice I hear that's been given to PhDs, on Twitter and elsewhere, just sounds to me like cheap motivational quotes. Quotes like, "Believe you can, and you're halfway there." Now, like these quotes, much of this advice that's being given around, it sounds really good, but when applied to your life, it has almost like zero cash value. There's nothing you can extract from it on a day-to-day basis. So after some reflection, I'm going to tell you 5 things that really made a difference for me for becoming a better researcher. All right, so let's start with the first rule: fail fast. Okay, now I think that at almost any time in a research project, your to-do list is filled with many, many tasks. And some of these tasks are kind of low stakes and are really good for procrastination. But some of these tasks are scary. Those are the tasks you're trying not to think about, you're trying to block. And because you're trying to block them, because these tasks might lead to failure. And failure is bad. But is it though? So consider this. If your project is successful at the end, right, in 10 weeks before CDPR, this means that there will be a finite amount of failures between you and the prize, which means that every failure you experience brings you closer to your goal. Otherwise, if there is some element that would prevent your project from succeeding at all, then wouldn't you want to know as soon as possible? So I think the logical conclusion from my flawless logic here is that, and this is something I try to do daily, is that you should really prioritize these scary tasks. You should maybe start each day with one of them, and also switch your attitude towards them. Because I think if you're not failing, you're probably not progressing. Okay, so rule 2, be experimental. Now, I think a lot of people, especially as they enter, their PhD or their masters, have this romantic view of a researcher of being this, brooding theoretician writing equations on a window with a marker, trying to solve the world's mysteries with the power of his mighty brain and his knowledge of integral calculus. But in reality, if you look at the history of science, you see that some of the greatest scientific breakthroughs were made by making sense of some natural phenomena observed in a lab or through a telescope, or even by accident, like the discovery of penicillin when Sir Alexander Fleming left his lab for a vacation, without cleaning anything, came back after and discovered that some mold had started to grow, which killed viruses. So therefore, my second rule is be more experimental. Play around with your hardware, try combining things in novel ways that you don't know what's going to happen or what to expect. And I think if you do that, you allow the opportunity for nature to surprise you with some unexpected behavior, which you can then exploit. I can tell you from personal experience that in almost any project, especially my best projects, there was some part of the project where something happened that I didn't expect just by playing around with the hardware and trying different things. Okay, rule number 3, incorporate fun and passion to your research. Now, look, I get it. Research can be hard. I mean, think about like in high school and undergrads, your life was so good. All you had to do is, find the correct answers for some given questions. But when doing research, you don't even know if there is an answer. Heck, you don't even know what the right question is. And you have to solve both of them. And this is why I found it very helpful to incorporate little elements of the things you enjoy into your research. And this could be little things like opting for some cool toys and demonstrations for your experiments, or trying to steer your project towards something you like doing, for example, like music or playing guitar. You would be surprised how these little choices can make a big difference to your day-to-day experience and make your life a little easier, especially as those hard weeks before the deadline arrive. Okay, so rule 4, results and presentation matter. Okay, if there's one rule I want you to take from this part, one rule that has the biggest bang for buck is that results and presentations matter. Now, you're probably thinking, well, of course they matter, Sherlock, like what a huge reveal. But no, you should really understand that the choice of the experiments you do and the way you present them will make a huge difference in the way your work is received. This is something I learned. Maybe even a bigger difference than it should be, but that's the way it is. Now, the people who review your paper are busy. They're trying to be done with your paper as fast as possible because they have other, mostly more important stuff to do. Your job is to spoon feed them results that crystallize why your method is great. So, for example, I see this all the time. If you claim to improve the image quality for some downstream vision task, show me the downstream vision task. Show me that performance. Don't waste anyone's time with endless metrics. Show the reviewers exactly what you promise in the introduction and abstract in the most exciting way possible, even if it means you have to wear embarrassing bodysuits around the campus. And also, the way you present your work is important too. Now, in a perfect world, your reviewers and your peers will judge you solely on the content of your work. But in the real world, the sooner you get to start learning some graphic software, the better. Okay, now for the final rule. Now, this rule is more of an opinion piece, and I'll explain it using a metaphor, so bear with me. So, a research project is a little like climbing a mountain. Your goal is to reach the peak, discover what's there, and tell everyone about it. Now, the discovery you make on that peak will be your contribution to science. But what if you knew that right behind you, there are 100 other climbers, all climbing for the same peak to discover the same secret? And suppose that it will take these climbers a week, a month, or even a year longer than you to get to the top. But they will get there eventually, for sure. Well, what does that do to your contribution to science? Well, if you ask my opinion, and this is my opinion alone, I would say that your contribution is significantly diminished. For the simple reason that whether you were climbing this mountain or not, the end result is going to be exactly the same, plus minus a month. But there is something else you can do, something I tried to do. You can try to find a different mountain that no one in the visible horizon is trying to climb. A crazy mountain that very few people thought of climbing. A mountain whose story would be so unique, it would stand out immediately in the stack of papers of reviewer 2, instantly giving you an advantage over all the other papers about the first mountain. If you succeed in topping that mountain, I think your contribution to science would be larger. And again, that's my opinion. And you might also make a discovery that no one in the immediate future was going to make. But of course, you might be afraid that you cannot find such a unique mountain all by yourself. Well, in that case, all you need to do is to believe you can, and you're halfway there. Thank you.
All right, let's thank Mark one last time for his great advice and his great talk. All right, so thank you everyone for joining this month's lecture, and we hope to see you again for the future lectures in this series as well.